I'm very excited to talk to you today about vapor pressure, mostly because it relates to dynamic equilibrium. And equilibrium is such an important concept in chemistry. It's really the entire field of chemistry is based around the idea of equilibrium. And it's so important, and in general chemistry series, it usually gets covered about midway through. So I always get really excited to talk about equilibrium because I finally feel like we're talking about chemistry. We're talking about why things happen the way that they do. We can start to predict why things will happen, how they will happen, what we can tweak to make them happen more efficiently, all those good things. So to introduce you to the concept, I like to talk about dynamic equilibrium in the context of vapor pressure. So let's talk a little bit about vapor pressure. All liquids have a layer of gas over them because no matter the temperature, there's always going to be some exchange of the particles of the liquid going into the gas phase at the surface. And so this gas layer over the surface, because we know this about gases, can exert a pressure onto the surface of that liquid. And that pressure is related to how much of it there is. So if we think about our gas laws, Dalton's law of partial pressures, for example, says that there's this direct relationship between how many particles of gas we have and the pressure that it exerts. So there's various characteristics then of liquids that can allow for more gas. So if they tend to be more volatile, if they produce more gas particles than other liquids, then they're going to have more gas on the surface of the liquid, which means that it's going to have a greater vapor pressure. So vapor pressure specifically, because vapor is something going from the liquid to a gas phase that is normally in the liquid phase, vapor pressure really refers to kind of a gas law situation, a partial pressure situation, but at that surface of a liquid. So that's really the key to all of this. So vapor pressure is the partial pressure. There's a couple things that we have to keep constant. First, we have to have a constant T, so I'm not messing with the temperature, because we know if we mess with the temperature, that's going to impact the pressure, right? It's also going to impact how many gas particles we have, because if we heat up the temperature, that moves things around a little bit more, which is going to give you more of my gas particles as well. So we have to keep the temperature the same, and we have to be over the surface of the liquid, and that system has to be at equilibrium. So the system of the liquid and the gas that's over it have to be at equilibrium. We say that it has to be a closed system, meaning that there are no external influences on it. That system is what we're defining kind of as what we're looking at here. And if it's at equilibrium, then we can talk about the vapor pressure. Now, equilibrium, dynamic equilibrium, is the state where the rates of two opposing processes are equal. Okay, it's the state where the rates of two opposing processes are equal. So by rate, we mean literally how quickly something is occurring. And by opposing processes, we mean kind of two things that are going in exactly the opposite direction of things. And we'll talk about this in the context of chemistry here, but I like to think about it visually as digging a hole. So I'm going to show off my very amazing art skills here. So this is obviously me in my lab coat with legs and a shovel, and I'm digging a hole, right? So I'm digging this hole, and I have some dirt on my shovel that I'm flinging out of here, right? And then I have this like pile of dirt here. Yeah, that's pretty good. So I have this pile of dirt that I'm flinging out of this hole, and you come along and you start bringing in more dirt, and you put it in back into the hole. You're filling in the hole. So we're doing two opposing things. I'm removing dirt from the hole. You're putting dirt back into the hole. Maybe you're digging from a pile over here, right? I picture it kind of Bugs Bunny and Elmer Fudd-esque, right? So one person is digging in, the other person is digging out. And depending on the rates at which we're doing this, then that's going to impact the size of the hole, okay? So if I'm digging faster than you are, then my pile over here is going to get bigger and my hole is going to get bigger, right? But if you're digging faster than I am, then your pile is going to get smaller and the hole is going to get smaller. But if we're digging at the exact same rate, Even though we're both digging, I'm digging dirt out, you're putting dirt in. If we're doing it at the exact same speed, then we're at equilibrium. It's the rate of two opposing processes that are equal. And we call that dynamic equilibrium because dynamic means changing. I also think of this as ongoing. So this is an ongoing process. It's not like, and now we are done. We have completed the equilibrium. We are done with the chemistry now. Everything has stopped. It's ongoing. The chemistry is occurring. It is in progress, but we're doing this at the same rate. And so the whole stays the same size. There's balance there. There's equilibrium. Equilibrium is sometimes used in that way in common speech, as kind of balance or regaining your equilibrium. Okay, so that's my highly sophisticated drawing to show you that. Let's try to do a little bit better and talk about some chemistry here. All right, if I have a flask here with liquid, these are my liquid particles that are in motion, as you can tell by my highly sophisticated motion lines. So these particles are moving around. If I put a stopper on this thing, which is what this is, even though it looks a little bit small, smallest stopper ever. So I put a little stopper in here, then that's going to start to contain any of the gas particles that were in there. So this is happening. These things are moving around right at the surface. These particles are leaving. And then at the same time, these particles are going to be kind of slowing down. They're going to be coming back towards the surface. Some of them are going to get pulled back into the liquid. So if we keep this temperature constant, so I'm not changing anything about the temperature, I'm not putting more heat into the system or anything like that, then this process is going to reach a point, so long as we have a closed system, I'm not allowing any new gases in and out, then it's going to reach a point where the rate of the liquid going to the gas is equal to the rate of the gas going to the liquid. So we'd say that the rate of vaporization, so that would be liquid to gas, is equal to the rate of condensation, which would be gas to liquid. Okay, so we have this rate of how quickly these particles are leaving and going out into this open air of the flask container. They can't totally leave, otherwise we wouldn't have a closed system. And then these particles that get pulled back into the liquid because of different attractive forces that cause these things to stick together, and they want to be kind of more in the liquid phase. Again, that sort of depends on the characteristics of the liquid itself. Then this rate is going to equilibrate. It's going to balance out. And when it does, we say that this is at dynamic equilibrium. Again, the dynamic means that this is an ongoing process. It's not like, and now there's that many molecules and nothing changes. These things are both ongoing. They are changing processes. Gases are becoming liquids, liquids are becoming gases, but they're happening at the same speed. If we think about this graphically, because we're scientists, so we always think in terms of graphs, then the rate of vaporization is actually going to slow down a little bit over time, right? So how quickly I'm going from a liquid to a gas here is going to start out pretty high, right? Because when I first cap it off, there were, here's the liquid, all the gas particles were leaving. Now I'm capping it off. Now I have this kind of process where I was just vaporizing, and now I'm not. I'm going to kind of steady out, and then I'll end up going at kind of a constant rate over time, right? Not a non-zero rate, but just a constant rate over time. So let's call that my rate of vaporization. So it started pretty fast, and then it slowed down a little bit. Now the condensation part's going to start really slow because my vaporization wasn't really happening, right? I just capped off the system, so there was no gas in there really to be condensing. So it starts off kind of slow, the rate, but then it's going to speed up, And ultimately, they're going to end up at the same place on my graph here. Hopefully you can kind of see my intermingling of lines. And this is my rate of condensation. And this place at which, kind of this point here where X marks the spot, where we end up with the equal rates, this time that it happens, this is my place of equilibrium. And once it reaches that, once those rates stay steady and stay equal to each other, then it stays in equilibrium. It stays balanced that way. The system likes being in equilibrium because it's very stable. It's going to reach that point, and this point is going to be different for different liquids, different gases, different solutions, and we'll kind of talk about in future videos different things that will impact that equilibrium and how we can account for that. Okay, pretty cool. I'm excited to talk about equilibrium. If you have any questions on it, don't hesitate to reach out. Otherwise, I'll talk to you again soon.